This is Module 5, Lesson 2. We're working on functions. We're going to be talking about how each function has, for each input, there's exactly one output, and we're going to look at how they're plotted. In this particular lesson, we're going to determine whether a relation is a function. We're going to complete data tables using functions. Then we're going to take word problems and we're going to create functions to describe the relationships and use the functions to predict values. All this can be found in the Eureka Workbook, Module 5, Lesson 2. Now, we're going to start out here. This is in your workbook. This is Lesson 2, Module 5, Lesson 2. This is the formal definition of a function. We talked on the last lesson about dropping a ball off a tall building. So let's say you got a tall building here, and someone's standing up here and they drop something off the building. So let's say they're going to drop a ball off the building, okay? Here's a ball falling off this building here. Now, what this says is let D be the distance traveled in time, T, right? T is in seconds. Here's our big D, here's our small t. They want us to use the equation D is equal to 16t squared to calculate the distance the stone dropped after a given time. Well, let's do just that. For this first one, if our t is 0.5, we would say D is equal to 16 times 0.5 squared. Put that into your calculator. 0.5 squared times 16. Then you get 4, okay? Work with me as we do this. That would mean after half a second, it has dropped 4 feet. Now let's see how far it's dropped after 1 second. So let's plug in 1. D is equal to 16 times 1 squared. Now we would know that 1 squared is 1, so 1 times 16 would be 16. Okay, now let's do this one. D is equal to 16 times 1.5 squared. Okay, so in your calculator, you do 1.5 squared multiplied by 16. 1.5 squared times 16 gives you 36. Okay, so after 1.5 seconds, this ball has dropped down 36 feet. How about after 2 seconds? Well, you might initially think, well, that should be twice this, should be 32. But remember, this ball is getting faster and our time is being squared. So let's simply put this in. This would be D is equal to 16 times 2 squared. 2 squared is 4. 4 times 16 would give us 64. So after 2 seconds, the ball will have dropped 64 feet. How about after 2.5 seconds? That would be D is equal to 16 times 2.5 squared. Okay, so I'm going to do 2.5 squared, multiply that by 16. And you get 100. After 2.5 seconds, that ball will have dropped a total of 100 feet. What about after 3 seconds? Okay, well, let's plug it in. Distance is equal to 16 times 3 squared. We know 3 squared is 9, so it would be 9 times 16. And you get 144. So after 3 seconds, it's dropped a total of 144 feet. How about 3.5 seconds? Distance is equal to 16 times 3.5 squared. If you put it in your calculator, 3.5 squared, then multiply that by 16. You've got 196. After 3.5 seconds, it's dropped a total of 196 feet. And then after 4 seconds, distance will be equal to 16 times your time, which is 4 seconds squared. 4 squared is 16, so you're talking about 16 times 16 there. And you get 256. So after 4 seconds, the ball has dropped 256 feet. Okay? Now, if you want to go back to the last lesson and see, these are the exact values that you saw in the last lesson. Does the function D equals 16t squared accurately represent the distance the stone fell after a given time t? In other words, does the function describe this rule assigned to the t correct distance? If you go back and look, it actually does, okay? It gives us the values that we got in our last lesson. But the main thing here is we've learned how to fill this out. Now I want you to notice something. This is not linear. We did this in the last lesson. Our rates of change here are not the same as you do these around. So this is not a linear equation, all right? This is something that is going to trend upward. Okay? Now let's look at these that we've got here, and we're going to talk about whether or not these are functions. We actually did some of this on our last lesson, so let's discuss about whether or not something would be a function here. We'll start with the first one. Remember, to decide if it's a function, if you've got x and y values, what you do is you check your x's. Are any of the x's repeated? And we talked about this. For something to be a function, for each input, there can only be one output. Well, here's our problem. Here we've got the input of 5 and the input of 5. See, this is like a little factory, and I have a function that occurs here. If I put in 5, this time I get out 19, don't I? Well, every time I put in 5, I should get out 19. But here it says if I put in 5 the second go around, I get out 20. That can't happen if it's a function. So this is not a function. Not a function. Why is it not a function? If it's a function, for each input, there would only be one output. In this case, we've got the input of 5. So here's our input, our x. And our output is 19 this time and 20 that one. It's not a function because input 5 has two different outputs, right? What are those two outputs? Well, here it had 19 and here it had 20, right? 19 and 20, okay? So this cannot be a function because input 5 has got two different outputs. Your best way to look at it is look at your inputs and see if any of them repeat and have the same output or have different outputs. But the reason it's not a function is because input 5 has got two different outputs. Let's look at this one, number 3. Can this table shown below represent values of a function? Do we have any repetition on our inputs? We do, right here. We've got an input of 7 for these two. Does the 7 have different outputs? Yes, it does. So this is not a function. Why is it not a function? Input 7 has two different outputs. What are those? 15 and 10. Okay, now let's look down here at this one. Can the table shown below represent values of a function? Well, let's look at our inputs, just our inputs. The outputs does not matter. Somebody's going to go, oh, but look, the outputs repeat. Output does not matter. You're just looking at inputs. Is there a repetition in your inputs? There is not. Each input has its own output. Each input has exactly one output. Doesn't matter that the 20 and the 10 both get 32 for the output. The x is not repeated here at all. So yes, this is a function. Why? Each input has only one output. Okay? Look at your x. Always look at your input. You're not worried about your output, you're worried about your input. Okay? Now let's look at number 5. It says, it takes Josephine 34 minutes to complete her homework assignment of 10 problems. So we've got 34 minutes, 10 problems. If we assume that she works at a constant rate, that means this is a linear equation. We can describe the situation using a function. So first, let's write a function for this because they're wanting us to predict how many problems she can complete in 25 minutes. This is a linear equation, has a constant rate, so it's going to be y is equal to mx plus b. Now we're going to start writing equations for our problems. We're going to start modeling the equations, the situations. Well, let's look at this, guys. When we're dealing with a linear equation, the two things we need to find is the b and the m. The b is where we start, where we begin. At time 0, how many problems has she worked? Well, it doesn't say she had any already worked, does it? So at time 0, she would have 0 problems worked. We know that our b is where we cross the y-axis, okay? It's the point 0b. So if there's 0 problems started at time 0, your b here is 0. Now we need to find the m, the slope. We know m is change in y over change in x, okay? We've got 34 minutes, 10 problems. Would this be 34 minutes per 10 problems or 10 problems per 34 minutes? You know, we put the time on the bottom in most cases. So this is 10 problems. The speed at which she's doing this is 10 problems in 34 minutes, okay? So our slope is 10 over 34. Our m is 10 over 34. I don't need to leave the plus b there, do we? Our equation would be y is equal to 10/34 times x, where x is what? X is your time. You can see it's right down here with the x's. Your y is your number of problems. You can tell if you write out your rate right there, your m, your slope. This is the equation. This is your function. Predict how many problems Josephine can complete in 25 minutes. So we got 25 minutes. Does 25 minutes go in for the x or the y? Well, it's pretty obvious that this is 10 problems per 34 minutes. You'd multiply that times the number of minutes to figure out how many problems. If you're not sure, though, look over here. See how we set up our slope here, our rate of change? The minutes correspond to the location of the x's. So minutes are the x's. We plug that in for our x. Y is equal to 10 over 34 times 25. Okay, we plugged it into the equation here. Now all you've got to do is put that into your calculator. 10 divided by 34 times 25, and that would give you 7.35. That would be 7.35. That means you solve 7.35 problems in 25 minutes, right? Now, let's keep going. We're just going straight through the book. Oops, shouldn't have erased that. This just says write the two variable linear equation that represents Josephine's constant rate of work. That was y is equal to 10 over 34 times x, where x is the number of minutes and y is the number of problems. Now use the equation you wrote as the formula for the function and then fill out the table below. Okay, so we're going to use this and fill out the table. There's a lot of times you'll be filling out tables. You're making points so you can plot the equation. If she plugged in 5 for here, she'd be finishing 1.47 problems. Now let's plug in 10. That would be 10 divided by 34 times 10. And that would give you 2.94. See, it says answer to the hundredths place. So in 10 minutes, she would have completed 2.94 problems, almost 3 problems, right? After 15 minutes, what would she have created? We're going to plug the 15 in for the x. 10 divided by 34 times 15 would give her 4.41. After 15 minutes, she would have completed about 4.41 problems. 20 minutes, let's plug it in. 10 divided by 34 times 20, and it would be 5.88. 5.88 problems, almost 6 problems, and then 25. 10 divided by 34 times 25, 7.35. That's what we got just a minute ago when we did 25 minutes, right? 7.35 problems. Does that make sense? If you can do 10 problems in 34 minutes, then you do less than 10 problems in 25 minutes. So that would be 7.35 would make sense. We've already done this. We compared that. Our 7.35 is the same thing we got before. On E, use the formula for part B and compute the number of problems completed when x is -7. Well, I can plug this in for x up here, okay, -7. And if I do, I get -2.06. But x stands for what? The time that it takes to complete problems. And y is the number of problems completed. So does it make sense to have -7 minutes or -2.06 problems? No, it doesn't. There is no such thing as -7 minutes. So although you can do the math, it doesn't make sense in this context. So you always have to remember what you're actually calculating. If x is -7 and x stands for time in minutes, then that doesn't make sense. Okay? All right. For this problem, we assume that Josephine worked at a constant rate. Do you think that's a reasonable assumption for this situation? Probably not, because some of the problems she'll work may be harder or easier than others. So she probably couldn't work problems at exactly a constant rate. Now, just to review the lesson itself, we have our little input-output machine, our little function machine. If you input a value, in this case, we were talking about the time to do problems, and then it would output the number of problems you would probably be able to finish. And your function goes right here, right? Okay, so let's play with some of the input-output materials here, okay? Problem sets. This is on the problem set page. This is on the homework page. I think it's page 21. Look and see. We're going to go through the problems in the problem set. First things here says the table below represents the number of minutes Francisco spends at the gym each day for a week. Does the data shown below represent values of a function? Is this a function? Now remember, when we're deciding if it's a function, we look at our input values, our x's in this case. We see if anything's repeated on this line. 1, 2, 3, 4, 5, 6, 7. No, nothing's repeated. Okay, so the reason that this is a function, it is a function. Okay, nothing repeated here, but the reason is because each input has only one output. Okay, that's the reason that's a function. Number 2, can the table below represent values of a function? Well, let's look and see. Are there any repetitions on our input? 9, 8, 7, 8. Oops. Yeah, right there and right there. Okay. This is not a function. We used our inputs to see, but we know it's not a function. And the reason is because there's 2 reasons actually. Input 9 has 2 different outputs. Input 9 has 2 different outputs. What are they? It'd be 11 and 28, right? Okay. And also input 8, right? Input 8 has two different outputs. What would those be? Okay, 15 and 24. So this definitely can't be a function. In fact, it's got 2 points that wouldn't work. Go to number 3. Right. Now we're going to decide whether or not a function actually fits a data table. All right, let's look at number 3. Erase a few of these so we can do this. Olivia examined the table of values shown below and stated that a possible rule to describe this function could be y is equal to negative 2x plus 9. Is she correct? Explain. Okay. Now, first off, I need to see if the points will fit on here. We're going to assume that this one's linear, okay, but we could check the slope to see for sure. We know that the slope, we need a slope of negative 2. Our slope would be change in y over change in x, all right? Let's see what the slopes are here. 17 minus 9 would be 8, right? Negative 4 minus 0 is negative 4. Slope here is 8 over negative 4, okay? That's negative 2. Let's check the slope here. All right. 9 minus 1 would be 8. 0 minus 4 is negative 4. Slope would be negative 2. So it fits right there. All of these slopes are negative 2. 1 minus negative 7, or let's see, we could go either way with this. Let's see which way we're going. Yeah, 1 minus negative 7 is 1 plus 7, that's 8. 4 minus 8 would be negative 4. That would be 8 divided by negative 4, which is negative 2. Same slope there, okay. Negative 7 minus negative 15 would give you a positive 8. Okay. 8 minus 12 will give you negative 4. Your slope is negative 2. And you're going to get negative 4. You're going to get a slope of negative 2 if you keep going down this whole line, guys. Okay. So our slope is negative 2. We can also look at this. Our y-intercept is 9. I've just proven that this fits. If you're not sure, you could plug in points to see. Okay, let's try plugging in some points. I just want you to see that you could do the same thing by plugging in some points. Okay, let's plug in a couple of points and see if these fit. We know that the slope is the same on every one of these. So let's see if some of these points will fit. Let's try this point and this one. I'm just trying these two because they look easy. There's no negative values in there. So let's plug these in and see if they work. If I try the point 0, 9, here's my x, here's my y. Is 9 equal to negative 2 times 0 plus 9? Is 9 equal to 0 plus 9? Yeah, 9 is equal to 9. So 0, 9, that point 0, 9 is a solution. That means it fits on the line, is a solution of this line here. Y is equal to negative 2x plus 9. In other words, it's on this line. Okay? Let's do another one. Let's plug in this point 4, 1. Here's your x, here's your y. Y is equal to negative 2x plus 9. Okay, your y is 1. 1 is equal to negative 2 times 4 plus 9. 1 is equal to negative 8 plus 9. 1's equal to negative 8 plus 9 is 1. This is true. So this point, 4, 1, is a solution of y is equal to negative 2x plus 9. Okay? Both those points are on the line. This equation does represent this data. Okay? We've shown it to you by finding the slope between the points and the y-intercept. We've shown it to you by plugging in 2 points and see if it worked. All right? Let's look at number 3. Peter said that the set of data in part A describes a function, but the set of data in part B does not. Do you agree? Explain why or why not. Is this a function? Look at your x values. There's no repetition. So yes, it is a function. I'm just going to say this. Is a function. How do we know that? Each input has only one output. How about the B here? Is this a function? Well, let's see. Do I have any oh, look right there on my x's. I have a repetition there, right? So this is not a function. Why? Input negative 3 has 2 outputs. What are they, guys? 14 and 2. Okay. Let's look at number 5. A function can be described by the rule y is equal to x squared plus 4. Determine the corresponding output for each given input. Now let's be very careful. I want to make sure you see this one. This is big on the calculator. Y is equal to x squared plus 4. If our x is negative 3, let's plug it in. Y is equal to, if your value is negative and you're squaring it, you have got to put this in parentheses before you put it in your calculator. Please try this in a calculator. You know that a negative 3 squared is negative 3 times negative 3, which is a positive 9. But if you don't put parentheses there, you will wind up with a negative 9 from your calculator. Try it. Put just this in, negative 3 squared. What you will wind up getting is a negative 9 because your calculator thinks you're squaring 3 and then making it negative. That's not the way you want to put it in. In fact, try it and see if it works. Then, guys, make sure you put this in parentheses. Negative 3, and outside your parentheses, squared, plus 4. When you do that, you should get 13. Okay? That's 9 plus 4, which is 13. Let's try negative 2. Y is equal to negative 2 squared plus 4. Negative 2 times negative 2 is positive 4. 4 plus 4 is 8. How about negative 1? Y is equal to negative 1 squared plus 4. Negative 1 squared is 1 plus 4, which gives you 5. How about 0? Y is equal to 0 squared plus 4. That's 0 plus 4, which is 4. Now let's do the 1. Y is equal to 1 squared plus 4. See, I don't need my parentheses when it's not a negative number. That would be 1 plus 4, which is 5. Oh, we're getting some of the same y values, but it's still a function because, see, the x values do not repeat. Okay? Y is equal to, let's try this, 2 squared plus 4. 2 squared is 4. That's 4 plus 4, which gives you 8. Y is equal to 3 squared plus 4, which is 9 plus 4, which is 13. Okay, we're just finding all our data in our data table, and then 4. Y is equal to 4 squared plus 4. 4 squared is 16 plus 4 would give you 20. Okay, All we've done is we filled in our data table so we could plot these points. Now let's look at number 6. Let's see what 6 is asking us to do. So all this is about linear functions here. 6 is asking us to examine the data in the table below. The inputs and outputs represent a situation where constant rate can be assumed. So that means it's a linear equation. Y is equal to mx plus b. Determine the rule that describes the function. Okay, so when we're doing a linear equation, we need the b and we need the m. We know when we're talking about the b, it's where it crosses that y-axis, right? And where it crosses the y-axis, this is the point 0, b. Do I have a point that has a 0 for the x? Let's look and see. Oops, there's one right there. That point is 0, 8, isn't it? So our b is 8. Put it in. Now we need to find our m. What we know about our m, our slope, is it's change in y over change in x. Let's pick 2 points. Doesn't matter which 2 points. I'm going to pick this one, and I'm just doing it because they're the smallest ones that don't have negatives to them. We know this data point is 0, 8. We know this one is 113. This is the x, that's the y. This is the x, that's the y. We need to find the difference in our y's. 13 minus 8 over the difference in our x's. 1 minus 0. 13 minus 8 is 5. 1 minus 0 is 1. My slope is 5. Y is equal to 5x plus 8. Or you can simply do this. You can use change in y over change in x here. You can say, okay, the difference, see, these are your y's. The difference in my y here is 18 minus 13, which is 5. So you started here and went back. The difference in my x's here is 2 minus 1, which is 1. 5 over 1, okay? You can get that either way, all right? Number 7. We're still working on linear equations or on functions. And on 7, this says, examine the data in the table below. The inputs represent the number of bags of candies purchased, and the outputs represent cost. See, bags of candy, cost. Determine the cost of 1 bag of candy, assuming the price per bag is the same, no matter how much candy is purchased. Then complete the table. Well, if 4 bags cost $5, and 0 bags should cost $0, right? Then shouldn't we be able to figure this out here? Couldn't we just simply say, $5 and divide that by 4 bags? Wouldn't that tell me what it costs per bag? If I do that, isn't that $1.25 per bag? So 1 bag would cost me $1.25. 2 bags, $2.50. You multiply $1.25 by 2. 3 bags, add another $1.25, and it's $3.75. Here's 4 bags and 5 bags. 6 bags, let's see, another $1.25 is $7.50. 7 bags, add another $1.25, you're at $8.75. Write the rule that describes the function. Y is equal to, we start with y is equal to mx plus b, right? Okay. At 0 bags, this would be 0. So we know plus 0 gives us nothing. So we're just down to y is equal to mx. And our slope, our rate of change is $1.25. That's what it's going up each time. Y is equal to $1.25. The cost is $1.25 times the number of bags. Y is equal to $1.25 times the number of bags. Can you determine the value of the output if the input is -4? Well, let's see. Yeah. Y is equal to $1.25 times -4. Wouldn't that give you -5? Be -$5, right? Okay, does an input of -4 make any sense? Does -4 bags of candy make any sense? No. There is no -4 bags of candy. Okay, so in this context, this does not make sense. Okay. Now let's skip 8 and let's look at 9. Write a brief explanation to a classmate who was absent today about why the table in part A is a function and the table of part B is not. Well, let's look and see. Look at our x's. There's no repetition, is there, right? This is a function. Why? Because each input has only one output. How about this one? 1, 6, -9, -2, 1. Oh, 1 has been repeated, hasn't it? Okay. Not a function. Why is it not a function? Okay, it's because input 1 has 2 outputs. And what are those? 2 and 19. Okay? All right, guys, that covers everything we're going to cover on this lesson.